The last thing I want to talk about in the first part of the lecture is, remember, we have after solution of U asterisk Q asterisk, name it as you like. I used to name this equal to B, sorry, this is curly bracket, this is known, this is known, this is unknown, solve, get phi. You can compute U at any point Y equal to sigma over the sources U asterisk of x and xi I times the phi of xi I. Okay? And we can differentiate with respect to x alpha of x. We will get du of y by dx alpha of x equal to this part. We are going to differentiate it because it has x. It will give sigma over I du asterisk of y. This is y, I'm sorry. As far as use y. Y, sorry, I'm sorry. Y. And xi I times dx alpha of point y times the phi of xi I. And these values are constant. Okay? And we can multiply by n alpha at y, provided that the point y is on the boundary. But if point y is not on the boundary, we don't have normal. Okay, we'll get q asterisk of y, sorry, q of y. We'll get q of y equals sigma over I q asterisk, because the multiplication of this term by n alpha will give us q asterisk of y and xi I times the phi of xi I. Okay, so at any internal point, we can compute at any point y, we can compute this value. We can't compute q of y because we don't have normal. We don't have normal inside, except when I defined line like this, I want to compute q of y in this direction. Now I have a normal. And of course, q in this direction will be opposite than q in the other direction, according to the normal that you're going to use. Last point before we get rest or something like that. The last point, when we have u of x equal to, these are the source, these are the discrete method of fundamental solution between u asterisk of x and the xi I, phi of xi I, and the q of x equal sigma over I q asterisk of x and xi I, phi of xi I. This is provided that these sources are discrete, but sometimes we have these sources are continuous sources. This is discrete sources. Now continuous sources. The continuous sources, here I have my point, and I have, this is my domain, and this is my boundary, and I have sources here outside, and this boundary for the sources, I'm going to give it to S of xi, and this is the domain of y, and this is the boundary of x. So when we have point x, it is on the boundary. We have point y, it is inside the domain. We have point on the source boundary. I'm going to choose continuous sources. I'm going to give it xi. This equation will change like this. U of x equal integral of the boundary of S of xi times u asterisk between x and xi. There is nothing called xi now because it's continuous. No more discrete sources, times the phi of xi. Okay? And I don't write the ds of xi. It's much better to write here ds of xi, but I don't write. And when we differentiated and multiply, we differentiated with respect to the coordinate of the point x, we'll get q of x equal integral over s of xi, q asterisk of x and xi phi of xi. And I'm saying very easy differentiate and move the derivatives operator inside the integral operator. So I should have very smooth kernels or something like that. Because of that, until now, the point xi is away, far away from, not far away, at least away from the point x. That xi and x will never coincide. This version, we call it indirect boundary element formulation, indirect regular boundary element formulation, or boundary, I like to say it, boundary integral equation formulation. Okay? Okay? So, now we can move the sources according to lines or according to closed contour outside. When the sources will come to be coincides on the boundary, we will have a problem. When the sources will come to be on the boundary, we have singular integrals, and as far as we have singular integrals, it's not easy to move the derivative inside the integral sign. We have to stop here. Okay? Until now, still there are two tricks. I'm going to cover them at the end of the lecture, but now we can have about 10 minutes break or something like that. Okay? I guess it's very, very clear until now. Okay, Paul?
Yes. Yeah.
Any questions?
Okay. Yeah, I think that the effective condition number is sometimes it works. It can help people to which can guide the user to the choosing the suitable element numbers. I think so.
Let me have some experience in it. When I met Professor Chan last summer, he convinced me totally to use it. And actually, when we work with the method fundamental solution, especially for hard problem or something like Navier-Stokes equation or something like that, you need a lot of number of points, and you will have a lot of air conditioning. So you would try to find any source of light inside this darkness to give you a clue or something like that to place where are the sources, where are the number of the sources. Let me see what we'll get.
Yeah. So sometimes the condition number cannot affect the all these issues, but the effective condition number, because they add the right-hand side vector in the in that. So I think the previous the people in Trifid's committee, they using this kind of method. I think the first
you mean Trifid's method or something like this?
Yeah, Trifid's method. Yeah, Trifid's method.
To be honest, I don't have really experience in this.
So I see it's Professor Zhuojia Li.
Okay.
Yeah, he did a lot of the work by using the condition number with the Trifid's method, and also he do some.
I like to read this. But
okay, so I understand.
In Trifid's method, you have another problem, because you use complete function, and with complete function is kind of homogeneous equation, and you increase the air conditioning.
Yeah. So and also the MFS someone do that like the CS and also the Liverlink if you know the from Hong Kong.
Okay.
Yeah. And but I will in our group we have also have to try, but in some other kind of method sometimes it doesn't work well. Yeah.
Okay.
So we can discuss and I can send you
Yes, please.
the some
Yes, please.
similar lectures. Yeah.
Okay.
Okay.
So
Yeah.
now I will take
So
10 minutes. 10 minutes
yeah.
break.
So see you all 10 minutes later. Yeah.
Okay. Bye.